My topic is structural integrity and life assessment of pressure vessels by using the risk-based approach. My co-author is Snezana Kirin, our scientific secretary, one of three. I will start with this Bhopal disaster and tragedy once again. There are a couple of terrible numbers that should never happen again, and we should contribute significantly to that. I mean, by we, ASIS and the community dealing with fracture and fatigue. And just to mention this last sentence here, it was really a big irony of this disaster that practically at the same time in New Delhi, couple of hundreds of kilometers away, there was the 6th International Congress on Fracture going on. I was there, and that is the world's largest conference of the kind. So let's see how we can prevent it. To start with this lecture, let me say a couple of introductory words. Where do we really need structural integrity based, of course, on fracture mechanics parameters and also life is stated here. It is, of course, I'm dealing with pressure vessels. This lecture is about pressure vessels, but more specifically, I'm dealing mostly with the situations when non-acceptable defects are revealed by non-destructive testing methods, and then repair with eventual waterproof testing is needed. And just a small digression, if I may, this is actually how structural integrity was born. It was back in 70s, last century, a large oil pipeline from Alaska to central USA had extremely large number of non-acceptable defects. At that time, they were called non-allowable defects, and they didn't know what to do. It was about the same price to repair all these defects with not very certain result, and or to build a new pipeline. So they decided at that time, and that was approved by state authorities, to check all these defects by fracture mechanics parameters and to find out if they are really non-acceptable, not only by standards, but really by knowing how they would behave during service. And by using that concept, only 10% of these defects were really repaired at the end of the day. So something like that is explained here in some details. What we have to consider is not only engineering view of the problem, but also we have to take into account that somebody has to make a decision, and most probably this is management, the owner of the facility. Like in the previously just mentioned case of Alaska Pipeline, it was the state, USA state, Department of Energy, more concretely. But in any case, it is up to us, engineers and experts in fracture mechanics, to present the case to the management. And then either they will decide, or maybe we will all together decide. But the whole story today is about the approach that is relatively simple. We can call it engineering approach that can allow management to make a reliable decision. So this relatively simple approach is presented in a form of risk matrix. I will show it soon. And we can also incorporate in a simple way some important effects like residual stresses and especially this waterproof testing. I'll come back later to that. So if we use analytical procedures, which are of course the simplest, or let's say engineering approach, from time to time we should of course verify them by more precise numerical methods or experimental research, and I will also present one case like that. So once again, TC12, this is our topic, deals with large critical constructions, including pressure vessels, and our basic aim is to prevent catastrophic consequences. I will present two cases with potential catastrophic consequences in static case, and just not to mention Bhopal once again. So in this introductory part, let me now explain what we mean by risk-based approach and risk matrix. The simplest way to present it is to use definition of risk as being product of probability and consequence. So even though probability might be very low, if we have potential catastrophe, then there is a certain risk. And in case of large pressure vessels that contain some harmful medium or could bring down a whole construction, as you will see later on, the consequence category is typically the highest one. And that is why this risk matrix has these red letters in the column far on the right side. So risk matrix is practically 5 times 5 matrix. It is arbitrarily constructed. First of all, consequence and probability categories need not necessarily be 5 of them, but that is really commonly used. Then again, we also, once we construct this matrix, it is a bit arbitrary, where we would put very low risk, medium risk, high risk, very high risk, or extremely high risk. Those terms are arbitrary, and in any case, when probability category is high and consequence category is high, or the highest ones, then of course we have very high or extreme risk. Contrary to that, when they are both low, we have very low risk. Now, in more details, the same risk matrix is shown here, and we have consequence of failure category, which is described here in terms of health, safety, environment, business security, image loss, and public disruption, and also probability of failure, which is here given in the simplest possible way, and that is the probability as number of events per year of divided by some reference number. So for the consequence, it is relatively simple in our case because it will be typically the highest one, but probability is really tricky. First of all, this previous experience as defined as number of events in certain period of time divided by total number of something, that's really useless in my opinion. once we check literature and existing options for probability assessment, we find out about two of them as the most popular and probably the most useful. This is API 581, that's standard for quantitative risk-based inspection as given by American Petroleum Institute, and then RIMAP, which is European competitor on the same subject. Anyhow, as I will show in some details in the following slides, both of them are relatively complicated. And we will actually use some other approach, something that we introduced, which is based on fracture mechanics principles and structure integrity and life assessment. Also, one important issue, which will be very shortly covered, is human factor, which we can also take into account. So for AP 581, we can say that it is very well established procedure. It is very useful and popular, but there are 4 sections, 654 pages. I guess 7 days of instructions minimum, experience at least 1 year minimum, and data collection would need typically a couple of weeks. You can check it, this PDF is available. So it is too complicated, especially if we need a fast answer. And once we find non-acceptable defect in, let's say, welded joint of a pressure vessel, we certainly need a fast and reliable answer. So what we focus more would be this ISO 31000 approach, not in general sense, but in a sense of procedures. They mention as possibilities to estimate probability. So the first one is already mentioned, relevant historical data, which is oversimplified and which does not reflect a current state of a component or structure, so we forget about it. The second one is typically used by RIMAP and AP 581, and it uses predictive techniques such as fault reanalysis, event reanalysis, and all other simulation techniques, which is too complicated in our opinion. So we will use the third option that is mentioned by ISO 31000 approach, which is expert opinion. And this is practically the approach that we introduced in this story. So what is it about? I guess you all know failure analysis diagram. That is maybe the most useful engineering tool that we have at our hands once we try to assess structural integrity of a component. It takes into account in a relatively simple way both the brittle fracture, potential brittle fracture, and plastic collapse, fracture caused by plastic collapse. Since pressure vessels are made of structural steels, typically low alloyed high strength steels, those are somewhat susceptible to brittle fracture, but certainly they would always have some kind of plastic, even a large plastic deformation before eventual failure. So from that point of view, failure analysis diagram is ideal, simple tool to analyze pressure vessel structure integrity. Now, in this diagram, we use so-called, our starting point is so-called Dugdale model. It was, here it is written, Dugdale plastic or yielding strip model. It is based on yielding strip for a true crack in infinite plate, and the governing equation for this is given here. This is kind of a limit curve where our fracture mechanics parameters are involved. Of course, stress intensity factor, K effective, which is based on CTOT, but it's introduced instead of it. And then yield stress, which is more generally used as the plastic collapse or critical stress. And then finally, stress, as shown here, which is denoted by sigma. Both stress intensity factor and its critical value are taken as the ratio, you can see it here, and then net stress in a cross-section where the defect is discovered, and critical stress are also taken as the ratio, in both cases non-dimensional ratios, which are then correlated in the way presented here. And this is actually the limit curve, which is here drawn in a diagram where non-dimensional ratios are given as x and y axis. So plastic collapse, probability of plastic collapse is increasing along x axis, and if it is more than 1, then we consider collapse as a very possible event. And then if we look at the y-axis, along y-axis, if we go from 0 to 1, there is an increase in a probability of brittle failure. So in this area, we consider brittle fracture as an option. Now, of course, in whole this area, we have unsafe situation for our component, but since we use a conservative approach both for collapse, plastic collapse and brittle fracture assessment, it is not given that component will fail here. It is just unsafe region. And contrary to that, in this whole area, we can say that our structure is safe from fracture because we estimated both brittle fracture and plastic collapse in a conservative way. So by describing failure assessment diagram in this way, we can now define what we mean by probability in the case of structural integrity assessment. If you look at this diagram, this point A is corresponding to the service parameters. And if there is non-acceptable defect with known dimensions, we can calculate both SR, which is X coordinate, and then KR, which is Y coordinate, and we can position our point somewhere on a diagram. Let's say it is positioned here. So it is quite reasonable to assume that if this point is close to 0, that probability of failure is close to 0, and vice versa. If we go all the way to the limit curve and get to the point B, probability becomes practically 1. So we can define probability of a failure according to this diagram and according to the position of the point. We can define it as OA divided by OB. And that is as simple as you can imagine, but still based on a sound fracture mechanics concept. On the other hand, if we would like to assess structural life and prevent, let's say, fatigue failure, we can use a diagram as shown here, crack length versus number of cycles. We can, in a way, follow how crack grows with repeating cycles with certain amplitude of stresses. And of course, either by knowing the critical crack length or looking simply at this diagram, we can see what is the critical situation, what is the critical number of cycles. In this case, shown here, it is about 2 million and let's say 30,000. So any point here along this curve has its own probability because it represents the spent life. And once we divide the spent life with the total critical life, we get this simple estimation of probability for structural life. So now let's go and check a few case studies. This one is more than 20 years old. It all started back in 1998. It is a typical problem, as I explained in the introduction. Regular NDT control revealed unacceptable defects. It was quite a surprise for the owner of the pressure vessel, actually 8 of them. There are 8 of vessels like this. They are used for high compressed air, which is then used to start large pumps, which are used to pump water up the hill. This is all part of third largest world reversible hydroelectric power plant. It is in Serbia at Drina River. It is very high pressure. Inside you will see concrete data. And it was working for about 20 years when these unacceptable defects were revealed. That was the surprise, because all evidence indicated that these defects were there from very beginning. First of all, there is no fatigue. Then there is practically no corrosion and any other mechanism of potential crack growth. This is a typical simple static case and simple geometry. Cylindrical pressure vessel, no inlets, outlets, nothing close to these defects. So we used fracture mechanics parameters and some engineering reasoning to assess structural integrity of 3 out of 8 pressure vessels. 3 defects were taken as the most important, and all of them are presented in one vessel because it would be kind of stupid to now make a sketch of 3 vessels because they are all the same. So just as if they were in the one vessel and they are all in welded joints. This one is along longitudinal welded joint, and these 2 are along circumferential welded joints. The first one, marked as 970/64, was probably the most dangerous, because actually it was they were revealed by radiography, and later on they were also ultrasonically examined, and only this one was confirmed by ultrasound. So this is why I will focus mostly on that one. It was practically incomplete penetration. This is 50 millimeter stick, so it was welded from two sides, and incomplete penetration is not a big surprise in that case. So it was 60 millimeters long and 2 millimeter wide, and it was unacceptable by standards at that time, and even as today's standards. Being such, all three of them actually needed this additional checking, and it was accepted by the authorities that they will make a decision according to our findings. So we used a conservative approach. First of all, for all three of them, we consider them as being along, let me go back for a second. For example, for this one, we assume that it is actually going along the whole vessel, or at least to be long enough that we can consider it in the cross section. So if we make a cross section, then practically this 2 millimeter wide dimension is length in the cross section in the segment that can be considered as a central crack in remote tension. Not to go into all details, but certainly it is a conservative approach. Surface crack, as it is in reality, would certainly behave better than what we have assumed. The same approach was used for other two, but they were not that critical, so we will skip them. So how do we actually proceed from that point? One issue is crack, sorry, not crack, defect itself, which we assumed to be all the way along the vessel. So that is the first conservative approach about its geometry. And then the second conservative approach is that we considered this defect as a crack, not as just lack of penetration. Then on the other hand side, we had to consider carefully fracture toughness. Fracture toughness we could not determine. We didn't have any material to do so. Unfortunately, they did not make any samples when they produced pressure vessels. But on the other hand side, the fortunate circumstance was that at the same time, or years before actually, for the same material and the same welding process, there was a doctoral study and extensive research about fracture toughness of all regions in welded joints. So by this fortunate circumstance, we actually had reliable and conservative data about fracture toughness of the most critical regions in welded joints, and these are heat affected zone, and then to some extent weld metal itself. Therefore, knowing also that corrosion and fatigue were not an issue, But keeping in mind that residual stress might be an issue because we didn't know if there was any kind of post-weld heat treatment, we used the following data. Vessel geometry, that was at least something reliable, material of the vessel, low alloyed steel with high strength, about 500 megapascals for yield strength, so-called second generation. Nowadays, low alloyed high strength steels are certainly less susceptible to cracking. This second generation steel was a bit more susceptible to cracking than we would like. Welding had to be performed very careful, and we knew about the team who did it, and they were good, but still, just to mention that we didn't know if post-weld heat treatment was performed or not. So we had to use the worst case scenario for material property, for fracture toughness. Crack geometry, as already explained, was taken as the conservative way. And then for the loading, internal pressure was well known, that was not a problem. But then we assumed there is a residual stress, and that would be the highest value. The good news was that we always had to take care to take into consideration just 40% of yield strength, because crack was positioned in such a way that less pronounced component of residual stress was perpendicular to the crack. And finally, for the fracture toughness, we used the least value that was established during the research I just mentioned. So it was about 50 megapascal square root meter, or as you can see in these units, 1580. So now we can perform some simple analysis, which goes like this. We calculate K1, taking into account residual stresses, and we get 663. We divide that by 1580, we get just 42%, and that is the practical probability of brittle fracture in our approach. And then we calculate net stress divided by critical stress, and we get X component of our service point. So the point would be somewhere here. It is 0.32 or 33. It states here 0.32 and later on as well, but in the sketch is 33. It really doesn't matter. And for the y coordinated 0.59. Once we take into account also, I skipped over it, so I'm back now, the measuring uncertainty. So yet another conservativity in this approach is that we take crack length, which is those 2 millimeters, twice as much because of measuring uncertainty, and in that case we will get 59%. Otherwise it was 42. So there are all kind of different values here based on different input parameters, but our conservative approach was like this. Other two points are given here for other two defects. So now we also take into account yet another additional effect, which is very important, which is waterproof pressure. Now, to take it into account practically means to increase net stress by 43%, and by doing so, both coordinates will change. You can see it from this, let's call it basic point. It would shift to this point, or if we just take into account residual effect, it will shift to this point, or if we take into account both effects, it would shift to this point. Now, for all these points, we can calculate probability as explained, and by doing so, we get probability 0.48 for this point, or 0.60 for this one, or 0.67 for that one, or 0.84 for this one. And now, knowing that consequence is certainly at highest value, because eventual failure and explosion could bring down the whole hydropower plant, well, theoretically, but it's possible. So we have to take consequence category as the highest one. Then our risk estimation is high at best. That means if we have no residual stress effects, and if we have no overpressurizing effects. If we have only one of these two, our risk category and estimation is very high, and then if we have both of them, we get to the extremely high risk assessment. That actually means that pressure-proof test should be avoided at any cost. One significant issue of this story is about this pressure-proof test. In our view, it does not prove anything, but it can make a lot of damage. The problem is in provoking micro cracks, because the typical steel used for large pressure vessel is welded joints, especially, are susceptible to cracking, and they should not be over pressurized. The simple fact that this proof test was successful practically means nothing. On the contrary, it is a kind of a mechanism to introduce microcracks, which may then grow to cracks and make, in best case, leakage, not to mention other potential consequences. So I think I'm a bit losing my pace. I mean, time is running too fast. So I will let this case study for you to read about it, especially since there is a list of references at the end of this presentation, so you can find a paper with the details, because it is about the same story, and also it is focused on proof test. And once again, we have shown that proof test is really useless and potentially harmful. So it is about the same procedure, the same reasoning, a bit of different material, different, of course, pressure vessel. It is storage tank. It is critical because it contains ammonia, so its consequences are also catastrophic. And you can really check on your own all this calculation. Now, just 1 minute on a survey about human factor effects. This so far presented was purely technical. And now for the human factor, we need a kind of survey. It has been conducted in one doctoral thesis, and with a number of questions and a bit complicated scheme for answering. Statistical analysis can prove, and statistical analysis can be used to evaluate risk which is due to human error. Now, result in this case was about 27% of a risk, and by combining two probabilities into one, we can see that in the case of probability 39.5% from mechanical fracture mechanics point of view, and from this point of view, human resources, we end up with increased probability to 0.56. But this is not the main focus. This is just that you see what else can be done. Now, case study 3 is something that I still want you to focus your attention. It is oil rig drilling pipe, certainly not a potentially catastrophic failure. So we will now deal with something like medium consequence. But interesting issue here is how we deal with fatigue. So we know that pressure is going from maximum 10 to minimum 7.89 megapascals. So there is an amplitude of loading. We know the number of strikes. We know all dimensions. So working stresses are 190 and 150. Amplitude is 40. This is the geometry. And actually, in this case, we tested two pipes, old and new. With new one, we made artificial crack with 200 millimeters long defect, which is half the thickness into depth. So 3.5 millimeters out of 7, which is the thickness approximately. And there was extensive research about this, another doctoral thesis. We have measured J integral by measuring strains. It is so-called direct measurement of J integral. And also we made a numerical study, three-dimensional finite element method, including XFEM later on to calculate fatigue crack growth. Some of the results are presented here. You can see that we once again applied this failure assessment diagram to analytically assess risk. And you can see once again some of operating points. Whereas you can see in this case that we also have some results for finite element method and for the experiment. They are in good agreement. And then we compare them. This is the main message from case study 3. So analytical assessment gives risk at a level of 69%. Numerical goes from 45 to 54 and experimental to 38. And we hold the experimental to be the most precise and numerical to certainly be more precise than analytical, or better to say less conservative. So keep in mind that by using conservative analytical as procedure, you will get the highest risk, or we can say we will get risk, unrealistically high risk. Anyhow, if this conservative approach still provides low enough risk, then we are sure that we can use our component on and on. Now, when I say on and on, that is static. But for fatigue, we always have to be careful. We need to check crack length depending on number of cycles, or we need to check what is the spent life in comparison with the total life. So this was done also here first analytically by integrating Paris law. You can see Paris law and this integration. Of course, we need either simple geometry or to simplify geometry to be able to do it in this way. And even in that way, we should take care about changing a geometric coefficient with increasing crack length, but anyhow, that is not a big deal. So once we apply this procedure, we can find out what would be the dependence of number of cycles on initial crack length and stress amplitude. Although we knew that stress amplitude is 21, we wanted to check what would be with 20, what would be with 25. And then again, although we knew that initial crack length was looking into the depth, because once again, we are looking at the cross section. 3.5, we also wanted to check what would be the case with 4 and 4.5 millimeters. And knowing that critical crack length would be 4.8. So number of cycles is given here. It is in millions. And once we divide that number of cycles with number of cycles per year, we then get years to go. For example, the best case is with the initial crack 3.5 and the amplitude stress 20, then we have almost 9 years to go. But with 4.5 millimeters and 25 megapascals of amplitude stress, we are actually already done with this component after 2/3 of the year. So this component cannot run more than 8 months in this case. So this is what we can get in conservative and simple way. So remaining life, which is the inverse value of these, are shown here and then put into consequence category that I explained. It's not the highest, but the next one. And here are the remaining life probabilities nicely shown in a way that they increase the risk from green one, which is low, to the yellow one, red one, and then this alarming, which is more than 1. Now, as I told you, it was a very simple way to do it, integration of Paris law for the crack that would grow into the depth. So cross-section and as if the length was all over the pressure vessel. But then again, we need some verification for that, and this is why we used XFAM. And then in that case, we used the real geometry. You can see it here. And this was done for another virtual crack that would grow from initial length of 1 millimeter up to, in this case, 142. And you can see here that XFAM provides about 2.5 or up to 2 times more life than the conservative analytical approach. That was something that we really expected because, as I told you, this analytical approach was too conservative. So, in conclusions, I think I persuaded you that risk-based approach can be very useful tool for assessment of structural integrity, that failure assessment diagrams can be used in static cases, and that we should forget about proof testing for the critical pressure vessels. Then that for structural life, we can use Paris law in case of simple geometries. That analytical calculation tend to be conservative, even in simple cases. So from time to time, we should definitely use either numerical or experimental method to verify our analytical procedures. And finally, and I guess in this approach the most important, that risk-based analysis can bridge the gap between engineers and managers, because engineers do not know what is the general situation about some kind of plant, and managers, they know that, but they don't know what is the real situation with the component. So these two teams should work together to come to the best solution to the problem. And references are also given here. You have this presentation on our site. So I will now stop my presentation and be back with you.